Now we're going to take up one more problem on thermal stresses. Problem number 59, and it reads as: at room temperature, the gap between bar A and bar B shown in figure is 0.25. So this is the bar A and this is bar B, which is 0.25 at the room temperature. What are the stresses induced in the bars if the temperature rises 35 degrees centigrade? So when you have the bar has been getting heated, so this will going to have a free expansion from here to here or from here to here. So given AA, that is area of cross section for bar A is 1000 mm square, and AB, A suffix B, area of cross section for the bar B as 800 mm square. The Young's modulus of bar A is 2 into 10 to the power of 5 Newton per mm square, and the Young's modulus of bar B, which is EB, will be equal to 1 into 10 to the power of 5. Given alpha A, which is coefficient of thermal expansion, 12 into 10 to the power of minus 6 per degree centigrade, and alpha B 20 into 10 to the power of minus 6 per degree centigrade. So IA, which will be equal to 400 mm, the length of A will be equal to 400 mm and length of the bar B will be equal to 300 mm. So to solve this problem, so here what happens is the free expansion. So that is alpha into T into L. So when you want to consider that is the general expression. So it will be here, the free expansion of bar A will be alpha A into T into LA plus the free expansion of bar B, alpha B into T into LB. So now that is what we got here. So we know what is the, so since you have the T as the common factor, so you take out T as the common factor, and then alpha A into LA plus alpha B into LB. So if you consider that and substitute the value of the temperature change, which is 35 into alpha A is 12 into 10 to the power of minus 6 into 400 plus 23 into 10 to the power of minus 6 into 300, the length of the bar B. So on simplification, you will go to get the free expansion as 0.4095 mm. So as the free expansion is restricted by the support, so therefore the compressive stresses are developed both in the bar A and bar B. However, the force in bar A must be equal to the force in the bar B. Yes. So for equilibrium condition, PS, that is PA is equal to PB, which is equal to P. So what is PA? PA is nothing but sigma A into area of cross section of bar A is equal to sigma B into area of cross section of the bar B, AB. So sigma A into, substitute the value of area of cross section of bar A as 1000, which is equal to sigma B into 800. Now on the simplification, sigma A will be equal to 0.8 into sigma B. So what is the contraction of bar A due to the temperature stress delta A, which will be equal to PA into LA by AA into EA. What is PA by AA, which is equal to sigma A into LA by EA. So what is sigma A, which is 0.8 into sigma B into length of the member. So you can take that is directly as sigma A into length of the member of bar A is 400 into 2 into 10 by 2 into 10 to the power of 5. So you can express that 2 into 10 to the power of minus 3 into sigma A on simplification. Similarly, if you want to go for the contraction of the bar B due to the temperature stress delta B, so what is the contraction of the bar B? Delta B will be equal to again PB into LB by AB into EB. So that is equal to sigma B into LB by EB. So you substitute the value of length of the bar B and the Young's modulus of the bar B. So that is sigma B into 300 divided by 1 into 10 to the power of 5. So on simplification, you will going to get 300 into 10 to the power of minus 5 into sigma B. Now also what we know is delta A plus delta B is equal to, what is that? The total expansion, that is delta A plus delta B 0.4095, that is the total expansion in the free expansion, minus the expansion restricted is minus 0.25. So then which will be equal to 0.1595. So for that we need to find out what is the value. So here 2 into 10 to the power of minus 3 into sigma A plus 300 into 10 to the power of minus 5 into sigma B, which will be equal to, what is that? 0.1595. But we know the value of sigma A, which is 0.8 into sigma B, that is 2 into 10 to the power of minus 3 into 0.8 into sigma B plus 300 into 10 to the power of minus 5 into sigma b, which will be equal to 0.1595. So on simplification, you are going to get the temperature stress induced in the bar B, which is sigma b, will be equal to 34.674 Newton per mm square, which is again, it is in compressive in nature. Similarly, what happens, the temperature stress induced in the bar A, which will be sigma A, which will be equal to 0.8 into sigma B, which is equal to 0.8 into 34.674, which will be 27.739 Newton per mm square. So this is how you will be able to find out the stresses in both bar A and bar B. Thank you.